What's good, biotech enthusiasts, and welcome back to another episode. Today, we're going to further our discussions on biosensors by exploring DNA biosensors. This is part 3 of the series. So, if you're ready, I'm ready. Let's break down DNA biosensors. Now, since we've already covered so much about biosensors, you probably have an idea of what it is and how it works. But if you don't, here's a quick recap. Biosensors comprise of a biological element and a transducer, as well as an amplifier. The targeted molecule, or analyte, interacts with the biological element and produces a signal that is picked up by the transducer, which converts it into a measurable electrical signal. This signal is then amplified by the amplifier. Alright, now that you're all caught up, let's talk about how DNA biosensors operate. Obviously, the biological element for the biosensor, in this case, is DNA. The rest of the biosensor remains mostly the same. Now, in order to understand the process behind how the biosensor targets the analyte, we need to understand the structure of DNA. You see, DNA is a double helix structure, meaning it has two strands. DNA is made up of four nucleotides: adenine, guanine, cytosine, and thymine. Adenine can only pair up with thymine, and guanine can only pair up with cytosine. Now, let's relate this with the biosensor. For example, if researchers want to understand if a certain gene is present, let's say GC8T, guanine, cytosine, adenine, and thymine, the DNA strand that they would attach to the biosensor would be the strand complementary to the original strand, which would give them CGTA, cytosine, guanine, thymine, adenine. Since both the strands would be complementary, they would attach to each other or hybridize and create a biological signal. But before this, remember, the researchers split up the DNA helix by disrupting the hydrogen bonds that keep it together using either heat or other chemicals to get the target gene impaired. Ha! Get it? Impaired? No? Anyways, now this biological signal is then picked up by the transducer and is converted into an electrical signal that becomes amplified. Building up on this, let's talk a bit about the biological signal produced upon the hybridization of the strands. You see, DNA is much more stable when it is hybridized, and this stability can be measured in different ways. Let's look at a few, shall we? First off, we have optical DNA biosensors. From the name itself, we can comprehend that it uses light. Upon reaching stability, the DNA's refractive index changes, and this change is measured by the optical transducer. It is especially useful since it can detect small amounts of DNA precisely. DNA biosensors have overwhelming potential to revolutionize our present medical standards. It has the ability to detect the genes of a hostile virus or bacteria in our body and can inform us before it begins to reproduce and spread for us to take appropriate action at the right time. With even more advancement, they would be capable of detecting the early signs of cancer by checking the presence of specific mutations in a particular gene associated with cancer. Well, folks, that's it for today. Hopefully, this episode opened your minds to the technological complexity and awesomeness of biosensors. Make sure to tune in next week for our final episode of the series where we'll cover immunosensors. If you enjoyed this episode and want to see more in the future, consider following the podcast. This is Biotech Breakdown signing out.